All right, let's let the magic happen. Any questions? All right. We have talked about gravitational force. And up till now, we've called it weight. This is chapter 9, by the way. Let's talk about the generalized force. Because I'm talking about the gravitational force between the Earth and the Sun. Well, weight doesn't really fit. I mean, what's the weight of the Earth? You can't really do that because you really need to be close to the other object. So if the Earth went crashing into the Sun, at some point you probably could talk about the weight of the Earth, but there is still a gravitational pull, because from Newton's first law, objects want to travel in a straight line. So if there were no gravitational pull on the Earth, as the Earth goes around, if the gravitational pull suddenly disappeared, the Earth would just go shooting off in a straight line. So whatever is happening between the Earth and Sun, so that's the Earth and that's the Sun, not from the scale. If you think about that, the Sun is giving off something that the Earth is sensing. Now, theoretically, they're called gravitons, but let's imagine that the Sun is giving off this pulse of gravitons out into the universe. So Mercury, which is close to it, is going to get the full brunt of these gravitons. Venus will get the next brunt. Earth is a little bit farther away, it gets the next group. And so this is how the Earth knows the Sun exists. But as these gravitons go out, they're out into an ever-increasing size of sphere, which means that whatever gravitons are given out in a pulse, they're given out, it basically gets diluted. The farther out you go, the less gravitons would hit the Earth. So it's like if I'm here and I'm giving a pulse out, that pulse gets bigger and it gets stretched thinner and thinner and thinner, and I'm only getting a small little bit. That way, if I'm closer, I would have gotten a much larger percentage of it, but I'm farther away. What I'm getting towards is the farther away you are, the fewer gravitons you'll be hit by. And so this gravitational bit is inversely proportional to the distance. It also depends on two other things. All forces have to have at least two objects involved. So mass of the Sun, mass of the Earth. I'll just keep it generic. Mass 1 and mass 2. And the only other thing remaining is some constant up front. The third thing, which some students will call gravity. This is known as the gravitational constant. Gravitational constant. If you look back, I don't think it doesn't happen as much as it used to, but it used to be called the universal gravitational constant. I'm going to put that in parentheses. Occasionally I might throw that in there. One of the reasons why it's not universal is really not necessarily appropriate is that we actually don't know if it is universal. It's rather presumptuous to look at what we have here on Earth and go, well, the entire universe is like that. We don't know. And this is equal to 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. Now, if you forget that, just look at the top of any quiz or test or in the textbook and it'll give it to you. There's one other thing that's missing. What? What is missing from that formula? we're trying to find a force. What do you know about forces?
Oh, they have a direction.
Yeah, there's no direction there, so I need to put a direction in there. So, what do you know about gravitational forces? Attractive or repulsive?
Attractive.
Yeah. So whatever the force on Earth is, it would be towards the sun, and there's a force on the sun towards the Earth. But we need to somehow indicate that the force on one of the objects is towards the other one. And so we bring in our radial unit vector, which we talked about last week, or Monday, last week, negative r hat, and we need to properly, this would be the force on 1 from 2, and that would be a 2 there. This is the force on mass 1 from mass 2. So some of that's just formality. Usually you can just think through it and go, oh, gravitational force, it attracts. So let's do some numbers. The force between me and the Earth. Now we could use it. The force between me and the Earth, and it helps if I'm not writing black on black. There we go. I can do weight is equal to mg. My mass is about 100 kilograms. G is we'll just do 9.8 meters per second squared. And I get 980 newtons. All right, that's chapter 2 stuff. Now we're going to do chapter 9 stuff. I can use that formula. Now I should come out with an answer that's very similar to that. If I don't, something's gone wrong. So I know that gravitational force is equal to big G, 6.67 times 10 to the negative 11, times the mass of one of them, Earth or me or the sun, and I'm going to go 100 kilograms, times mass of the sun, .9 times 10 to the 30th kilograms. I'll double check that one. 0.9, zero. There's not a textbook in here. Could someone look up on the phone just mass of sun? Divided by, what is the distance?
It's about 1.9. It's like 1.9891.
1.9891. Oh, so 1.99 times 10 to the 30th?
Yeah.
Okay. Memory partially correct. All right. What about the distance between me and the Earth?
Almost nothing.
Why do you say that?
Because you're touching, well, I guess if you're on like 30 stories. Maybe like 3 stories between you and the Earth right now.
Okay, so we could probably go 30 feet, 40 feet. So if I were outside touching the ground itself, what would the distance be?
0.
So if I divide it by 0, what happens?
It all, wait. Nothing, right?
What do you mean, nothing?
Like the numbers don't change.
You divide by 0? All right, so let's, okay, 1 over 1 is 1. 1 over, what's 1 over 0.5?
2.
1 over 0.1?
10.
So as my denominator gets smaller, what's happening to my fraction?
It's bigger.
Yeah. So if I make this incredibly small, what's happening to my force?
It's becoming a lot larger.
Yeah. So if I'm touching the ground, we're basically not, we're saying that the limit as we approach 0, as this gets smaller and smaller, my gravitational force goes huge. So if we are talking about the distance from me to the surface of the earth, then anytime you touch the earth, you would never be able to pull yourself off of it. So that is not the distance we're talking about. What should the distance be?
Oh, to the center of the earth?
Yes. So center of the earth, and that's 6.38 times 10 to the 6th meters squared. All right, at this point, who has a calculator? That's probably easier. Who's a calculator? We got 1, 2. All right, I want everyone to actually do this calculation because I have seen way too many people not know how to use the calculators when dealing with this. You got an answer already? Anyone with an answer yet?
Like 326 million.
326 million?
Point one.
Okay, this seems a bit huge.
Round about the same thing.
You got about 3. Did I forget something there? So that'd be 10 to the 30th. No? Yep, something's off.
I got the same thing.
You got
The same thing.
the same thing.
My number's bigger than that, but it's around the same.
Huh. Crystal?
Oh, no. Oh.
Okay.
2.08 times 10 to the 15.
Okay. This is very interesting. And I guess Crystal and Chikara,
Around the same.
you got that too. Let me look again here. 10, that's 10 to the 30th, so 19. Oh, my bad. I said sun, didn't I? Yeah, Earth. Sorry about that. That number there is wrong. I'm sorry for doubting you. 5.98 times 10 to the 24th. There we go. And if that's not right, we'll have to look up the mass of the Earth.
What, this is 5.98.
Times 10 to the 24th.
Okay.
979
9088055.
I'll just stop it there. What would the units be?
Would it be kilograms? No.
Alright, so that's meters, and we're squaring that, that's kilograms there, and this is, the units here are Newton meter squared per kilogram squared.
Would that just be kilograms squared then? Because wouldn't the Newton meters cancel out? Or no?
The newtons would not cancel out. Alright, hint, we're finding a force.
Is it just Newtons?
Yeah, just do it. The kilograms, that kilogram and that kilogram, and that kilogram and that kilogram cancels out with the kilogram squared. That meter squared cancels out with that meter squared, and what we're left with just newtons. All right, so we end up with pretty much the same thing. So it works in this situation, it actually should work in other situations. Now, there are some physicists, because why not? They are actually trying to see, is that really squared? Maybe it's 2.000000001 or 1.999999. And best they can do is the difference between that and 2, between the experimental values of 2 is less than 0.00000, however many zeros in a 1. So it really does seem to be squared. All right, so we have this gravitational force. So we can now expand this into satellites. All right, so I got Earth here. I got the moon. Why don't we just take something smaller? I have a satellite going around the Earth. We will assume it's a circular orbit. If it's not in reality, it's an elliptical orbit, but that math gets really complicated quickly. Circular orbit works close enough. So satellite's going around in a circle. Wait, what kind of motion is that if something travels in a circle? Yep. So I have a centripetal motion problem here, just this takes place in outer space. Let's do a force diagram. What are the forces acting on the satellite?
Could you say like the gravitational pull is like tension almost?
Say it again.
Could you say gravitational pull is almost like tension?
In this context, yes, the gravitational pull is the force. It's the generic gravitational pull. Now I could use mg, but I have no idea what g is out in space there. Why don't we make this distance here 2 times the radius of the Earth? Or, let's see, radius of the Earth is that. Let's make it 10 million meters. All right, any other forces acting on the satellite other than the gravitational force? Yes, no? Okay. Friction, we're not worried about friction in outer space. Tension, that means we got a rope or chain attached from the Earth to the satellite. That would be hard. Other, there's no other. Weight, well, that's gravitational force. And normal force, it's not touching anything. So that's it. I plug into F equals ma. So I have this gravitational force and a fading marker. This gravitational force is equal to the mass of the satellite times the acceleration of the satellite, but it's traveling in a circle, so this is centripetal acceleration. We get, so this is big G, mass of the Earth, mass of the satellite over that distance squared. the 10 million, is equal to mass of the satellite times V squared over R. Well, I can get rid of some stuff. What do I have common to both sides of the equation?
R, wait, no.
Yep, I got one of the R's. All right, so that R goes away, and one of those goes away. What else do I have in common to both sides?
Mass.
Which one?
Of the satellite.
Of the satellite. If you desperately need to have a mass there, you can just make it 1 kilogram. But the mass of the satellite is irrelevant here. It does not affect the motion of it. By the same token of taking two objects at different masses and dropping them, they fall at the same rate. So, let's fading. All right, so my equation is just reduced down to this big G times the mass of the Earth divided by the radius is equal to the speed squared. So let's figure out what the speed of the satellite is. So it's 6.67 times 10 to the negative 11th times mass of the Earth, 5.98 times 10 to the 24th, divided by 10 to the 7th power, that's 10 million squared. And what is that equal to? Yes, need to do some calculating there.